So welcome everyone. Today we'll be looking at some of the problems here from worksheet 7. You're free to use this video that I'll be uploading to sort of prepare for your the assessment. And yeah, basically what I've been trying to do since last week is to sort of give you as many problems as I can to prepare you for the assessment. So hopefully this small video helps you. Right, so let's look at question 1 here. So for question 1, we are asked to suppose that f is a continuous function in the interval from 0 to 1. And we're also supposed to consider that f of 0 is equal to f of 1. And the question is asking us to use the IVT, intermediate value theorem, to show that f of c is equal to f of c plus 1 over 2, right? For some value of c between 0 and 1 over 2. Okay, so how do we do that? Well, we can first say, let's say that we assume some function g of x that is equal to f of x plus 1 over 2 minus f of x being equal to 0. Okay, so we have that function. Now, we've already been told, right? We've already been told that f is continuous, right? So we can say since f is a continuous function, right? Since f is continuous on that interval that we're given from 0 to 1 over 2, right? Since f is continuous on this interval, right? We can say that therefore, right, this function g of x that we just defined right now is also continuous on the same interval. Okay. Why can we say that? Because, well, definitely g of x is a function of f of x, right? G of x is in this condition that we set here, g of x is expressed in terms of f of x. So we can clearly say that if f of x is continuous on this interval, then g of x has to be continuous on the same interval, right? So since we can tell that g of x is continuous on that interval, then we can say that if we look for the value of g of 0, right? We substitute 0 into g of x that we defined here. It will be, right, f of 1 over 2, f of 1 over 2 minus f of 0, right? And what is that equal to? We are not, we don't know, right? We don't, we're not very sure about what f of 1 over 2 is equal to, so we can sort of leave it like that. But now, let's see what happens if we do substitute 1 over 2. Okay, so if we do substitute 1 over 2 into this equation, now we have f of 1 minus f of 1 over 2. Right? But remember that we were told that f of 0 and f of 1, right, are equivalent in this interval, right? So they are equal. So you are perfectly allowed then to replace f of 1 in this equation by f of 0. Okay, so you're allowed to do this. So now when you do this, you can already see that this is basically the same as minus f of 1 over 2, right? Minus f of 0. And some of you might ask yourselves, how come we're allowed to say that f of 0 is equal to f of 1 when they told us this applies for the interval from 0 to 1, not the interval from 0 to 1 over 2? Well, then I would direct you to the fact that the interval from 0 to 1 is included into the interval from 0 to the interval from 0 to 1 over 2 is included inside the interval from 0 to 1. So whatever applies in the interval from 0 to 1 over 2 certainly applies in the interval from 0 to 1 as well, right? So since we've established that this g of 1 over 2 is equal to that, and g of 0 is equal to that. So whatever this value is, okay, so we don't really need to know the value of f of 1 over 2 and the value of f of 0 in the function itself, because we can clearly see that whatever this value, f of 1 over 2 is minus f of 0, right? It's of opposite sign to the value of f of minus f of 1 over 2 minus f of 0. Okay, so we can clearly see that these two values are of opposite sides, whatever the values are, right? So what's the conclusion here, right? So since g of 0, right, g of 0 and g of 1 over 2 are of opposite values, or rather of opposite signs, sorry, then by the definition of the intermediate value theorem, right, which I'm sure you guys can find, right, there exists some sort of C, right? There exists some C, right, that belongs to the same interval from 0 to 1 over 2, right, such that when you substitute f of c, when you substitute c into f of x, right, you have to find that is equal to 0. Because you can clearly see that from 0, when the function is going from x is equal to 0 to x is equal to 1 over 2, it's changing signs. So somewhere in the middle, it has to go through 0. Goes from let's say this when you evaluate this into the function f of x, you find a negative value, right? And therefore, when you pick the negative sign of a negative value, this here becomes positive. So it would be going from a negative value to a positive value. So somewhere in the middle, it went to 0, right? And that's the value of x that you're calling c, that you are assuming exists in that interval from 0 to 1 over 2, right? Because that's the definition of the IVT, right? And if since f of c is equal to 0, right, we have also defined that also means, right, in other words, that f of c plus 1 over 2, right, minus f of c as defined previously, right? We defined f of c is just a constant, but this is basically the same as g of x, right? F of c, which is equal to f of c plus 1 over 2 minus f of c, which is the same as g of c, basically, right? Is equal to 0, right? Which should make sense, right? Because you clearly have already found that by the intermediate value theorem, somewhere in between 0 and 1 over 2, there is a value c that makes this function equal to 0. Okay, so this is basically the end of question 1. You'll feel free to pause the video at any time and go through the same questions again, and then come back. Right? So now let's look at question 2. So for question 2, it's asking us to find the values of k and m for which the function, right, this function that is defined piecewise, right, f of x is equal to 1 minus x when x is less than or equal to 0, and is equal to x squared plus kx plus m when x is greater than 0. And this function they're telling you is continuous and differentiable everywhere. Okay, you guys know what continuous and differentiable means, so you can apply it to this function, right? So now we can clearly see that 1 minus x and x squared plus kx plus m are both polynomials. We have, you can clearly see that, right? And since the entire function is continuous, differentiable, everywhere basically, because you're looking at anything that is greater than 0 or less than 0, right? So it's continuous and differentiable everywhere, as they tell you here. Immediately you can say that then the two polynomials here are also continuous and differentiable everywhere, right? But now what's left for us to do is to find the continuity and the differentiability of this function here at the value of 0, right? Because you can clearly see that the function itself is defined anywhere between less than 0 and greater than 0. But we need to sort of understand what actually happens at the value x equal to 0. Okay, so firstly, let's evaluate the continuity at x equal to 0 for that function, right? Well, for this, we use what we've used before, our limits, right? So let's insert the limits. Right? We have the limit that as x tends to 0 from the negative sign, right? Basically from the left, as x tends to 0 from the from the lower side, the left side, f of x is therefore equal, this limit here is therefore equal to, remember what in this piecewise definition here, what applies to our case when x tends to 0 from a lower side of the of the point 0. Because remember, what you're trying to define is you need to find if the value, rather the function f of x that is given here has a limit on the left hand side of 0 and the right hand side of 0 that are equal, right? Such that when you find that limit, it should tell you already that the function is continuous, or rather at that point, right? That's the definition of continuity. You need to check for the limits of the function from the left-hand side of the particular value, and that value should be equal to the right-hand side of the to the limit on the right-hand side of the value. And by right and left, I mean positive and negative. So if I say 0 from z, that x approaches 0 from the negative side, it means it's a value that is close to 0 but negative, like minus 0.0001, for example, right? We've mentioned this before. And if I mention that x is tending to 0 from the positive side, then it's a value close to 0 but greater than 0. Okay. Then we know that this limit is equal to the limit as x tends to 0 from the negative side of 1 minus x, because remember, as x is tending to 0 from the negative side, that means that it's more or less less than or equal to 0, right? So this is the part of the piecewise function that applies here. Okay. So what is this equal to? Well, that is equal to 1, right? When you substitute the value of x. Okay. So now let's check the same thing from the right hand side now. Okay. Let's check the same thing for the right hand side. And remember, the right hand side is just the limits as x tends to 0 from the positive side of f of x, the same function. But now remember that as x tends to 0 from the positive side, this second part of the piecewise expression now applies, right? So you need to copy this. This is now what the value, this is now the value that our f function, of f of x function is. Okay, so let's just copy the f of x function first. And then paste it there, and then remove the f of x and paste in the value of our f of x, which is x squared plus km minus n. So now what happens when you substitute the value of, let's put brackets here so it's more clear. What happens when you substitute the value of x into this, right? It eliminates the first term, eliminates the second term, and then it leaves out m. So this gives you that. Right. But remember what we said at the beginning. We said that since this entire function is continuous, right? That's the definition. It is continuous and it is differentiable everywhere, right? From basically minus infinity to positive infinity, right? It means that each one of these polynomials is also continuous and differentiable, right? So we know from our continuity calculations, we have to have, right, for this function to be continuous, we have to have that the first limits that we found has to be equal to the second limits that we found, because remember, the definition of the continuity at the value of 0 means that the limit from the left hand side has to be equal to the limit of the to the right hand side. Okay. And so what this basically means, or rather what this is equivalent to, it basically means that 1 is equal to m, right? Or m is equal to 1. So the value of m has to be 1 for this function to be continuous at x is equal to 0. Right? So now let's check the differentiability, right? So we check the continuity at x is equal to 0. Let's now check the second part. Is this function f of x differentiable at x equal to 0? Okay, so checking the differentiability at x is equal to 0. And basically, you know that the differentiability just means that you have to find f prime, which, as I've mentioned before, f prime is just the derivative of f of x, right? You have to find the value of the derivative of f of x at 0, right? So now, so now what you do is you evaluate the value of f of x at 0 is equal of the derivative of f of x at 0 is equal to, just give me a minute, guys. Right. Sorry. Sorry about that. So, there's a lot of noise around. Okay. Right. So you have to define the value of f of x. All right. The derivative, the value of the derivative of f of x at 0, right? Which, when you find the derivative of f of x, right, it's basically equal at 0, right? Because remember, this is the parts now that we have to focus on, the piecewise portion of f of x that we have to focus on, because this applies, remember, this applies for the values of x that are less than 0, but are also sort of equal to 0, right? As close to 0. So this is the part that you have to, of the piecewise definition that you have to derive. So when you derive that, right? So let me just rewrite that so it makes more sense. Just give me a minute. When you derive that, let me just write f of x first. When you derive that, you have -1, right? And now when you're trying to find the value of this derivative at x is equal to 0, then you get -1, right? So that value now, okay, so I misspoke here. So this is when you're looking at f of x from the left-hand side, right? So when you look at f of x from the left-hand side, I'll just write it 0 and then put to the exponent of negative, right? So the derivative of f of x, from as x tends to 0 from the left-hand side, right? So let me just copy this. Hopefully, you guys can follow what I'm saying here. So that's the left-hand side. Now let's look at the right-hand side. So now when you try to apply the same logic to the right-hand side, we're trying to find out the derivative of the function of x as x tends to 0 from the right-hand side, right? Then you have to consider the second portion of the piecewise definition here, right? So when you derive that in terms of x, you should get 2x plus k. Okay, so I'm leaving the derivation to you guys because we've done it for quite some time, so it should be sort of easy to apply it. And then when you try to find this value now at x is equal to 0, right? Because remember, we are looking at the differentiability at x equal to 0. Then you find that that is equal to k. Okay. And remember, the same rule applies here for differentiability. You need for a function to be differentiable at a specific value, you need to be able to find the derivative, especially when for these piecewise functions. The value of the derivative of that function at that point from no, not at that point, but more like the value of the derivative of this function as x tends to that point from the left-hand side should be equal to the value of the derivative of this function as x tends to that point from the right-hand side, right? Which is what I wrote here. Okay, I know it's a mouthful, but if you just understand the notation here, it should make sense, right? And if this applies, okay, if this is the condition that has to be fulfilled for the differentiability to apply, then we know for sure that we found that the right-hand side, the left-hand side is equal to -1, right, from our previous calculations. And then the right-hand side is equal to k, meaning k is equal to -1. So we found the value of k and we find the value of m that make this piecewise function defined as is continuous and differentiable everywhere. So the key point that we had to figure out is it continuous and is it differentiable at the value of 0? We know what's happening around the value of 0, but what is actually happening at the value of 0? And this is what we were able to find here, right? So this is the end of question 2. Moving on to question 3. I think there might have been, yeah, it should be 3 here. Oh, sorry, 3, right. And hopefully, if you guys have any questions based on these questions, you can always uh, you can always just go back to this video and go through the same questions, right? So now let's try to look at this question again. It's basically a sort of a repetition of what we did here. So I'll just copy this. And since it's a preparation for your test, I'll just repeat the same process. So it's sort of understood well in case this comes up in the test, right? So here now we give it the function f of x that is defined piecewise again, but now around -1. -1 is the key point here. So we're trying to find the continuity of this function at -1 and the differentiability of the same function at -1, right? Again, the same applies here. The limits, we have to find the limits of the function as it tends to -1 from the left-hand side, right? Which is what I'm writing here. And what is that portion of the piecewise definition, right? At this point, you can pause the video and then try to figure out what that is. Okay, so I'm assuming that you tried it. So the portion of the piecewise definition that we have to focus on here is this part, right? It's approaching -1 from the left-hand side. So this is the section of the piecewise definition that applies here. There, so we can just paste it in there. And now, when we try to find, substitute the value of -1 there, what do we get? We get 2 times -1 cubed, which is just -1, so -2, -1, -3, plus 7, which is 4. And then now, when you apply the same logic to the right-hand side, as x tends to minus 1 from the right-hand side. Now you have to consider the other portion of the piecewise definition, which is that. Okay. So we have pasted in here, right? And when you substitute the value of x, right, you should get k, because remember, minus 1 substituted in here makes all of this 0, multiplied by m, which is just 0. So we left with k. Okay. And just a note, because I didn't mention it, but I mentioned it before. Since this function here that is defined piecewise is continuous, is said to be continuous and differentiable everywhere, we immediately know that this applies to these two polynomials as well. Okay, the two polynomials here that define the function, right? Okay, so now for the continuity to apply at minus 1, we have to find that the limit from the left-hand side is equal to the limit from the right-hand side. In other words, we have to find that 4 is equal to k. Okay. Now, if you're trying to determine the differentiability now at minus 1, then you have to find the value of the derivative of the function at minus 1. Okay, so just change that to minus 1. And from the negative side, and basically what you're trying to derive then is that. Good. Let's copy that into the bracket sign. And what's the derivative of this? We've done derivative multiple times now, so you should be easily able to solve this. So it's 6x squared plus 1. The 7 is a constant, so its derivative is equal to 0. When you now you evaluate this derivative at minus 1, right? When you evaluate it at minus 1, what do you get? Well, you get 6 times minus 1 squared, which is 1, 6 plus 1, which is 7. Okay. When you evaluate the derivative of the function as minus 1, then as x tends to minus 1 from the positive side now, then you have to consider the second part of the piece, rather this other part here of the piecewise definition. And when you derive it in terms of x, right, you can clearly see that what you will be left with here is m. Okay? That will be equal to m. And when you evaluate that, it's minus 1. It's just equal to m. Right? And you know that the rule for continuity is that for differentiability, sorry, is that the value of the derivative from the left-hand side should be equal to the value of the derivative from the right-hand side. And clearly found that therefore 7 has to be equal to 7, right? So that is basically the values, these are the two values of k and m that this function has to have for the continuity and differentiability to be applied everywhere. Okay, so we are done with that. At this point of the video, you are more than free to pause, go through the same thing that we did, and then you should be able to understand it quite well. Okay. Thank you. So moving on. Moving on to question 4. So question 4 is looking now at f of x is equal to 7x cubed plus ln x cubed. And we asked to show that this function has an inverse. on the interval from 0 to infinity, right? And the way we find that is, I'll refer you back to your notes, guys. Show you, you guys covered this in class. We find that this function has an inverse is you take its derivative, right? So let's take the derivative of this function. And what do we find when you get the derivative of that? It should be equal to 21 squared, right? Plus 3. Remember, chain rule, you are able to do this. 3x, sorry, 3 ln x squared divided by x, okay? And as you can see, right, for all values of x, right, that are within this interval, but also even outside the interval, you can clearly see, well, not outside the interval, but within this interval from 0 to infinity, you can clearly see that for all those values, this will be equal to, will be greater than 0, meaning it will be a positive value, right? For all the values of x that belong to this interval, right? Meaning, for each value of x that you plug into this function, you will get one unique value of f of x. Okay, one unique value of f of x. What does that mean exactly for um for f, right? It means, right? It means that f of x is, remember from the first part of the course that you did, is the one-to-one function. It is a one-to-one function. Okay. On this interval here from 0 to infinity. And therefore, right, f of x has to have an inverse because it's a one-to-one function. Right? You remember, you guys can go back to the definitions and the rules for a function to have an inverse and stuff, but this is basically it, right? So now, this next sub question is asking us to find the value of okay, so this is tricky. How do I pronounce this? So it's basically the derivative of the inverse of f of x, right? So we find the derivative of f of x, of the inverse of f of x, and then we evaluate it at a point, some points given 7, 2, 1, right? So now let's go back to how we look for inverses. You guys have done that in the first part of the course, so this should be straightforward for you. If you don't remember this, you can just brush up quickly on that and then come back to this problem. Okay, so you're free to pause the video here, attempt it on your own, and then press play, right? So here we have f of x is equal to that, so let's just put y is equal to 7x cubed 7x cubed plus ln x 12 cubed, right? So since we've already proven that this is a one-to-one function, right? And remember what the one-to-one means. For each value of x, we have a corresponding value of y of x, right? And since this is reciprocal one-to-one function, then you are allowed to say that therefore the following applies. The inverse of this function would be now x is equal to 7y cubed, right, plus ln y cubed. Okay. And so that would be the inverse of our specific function, right? And now when you evaluate this, when you use implicit differentiation, right, to evaluate this in terms of x, right, what do you get? Okay, let's just okay. So basically, when you derive the left-hand side, you will get 1. The derivative of x is 1. Remember, you are deriving in terms of x, and you're deriving this one here, right? So let me just type. Okay. So next, you derive this first term on the right-hand side. So which just becomes 7 times 3, 21, right? Y squared dy over dx. Okay. Remember implicit differentiation. And then the right-hand side becomes ln y squared, 3 ln y squared, right? Multiplied by 1 over 1 over y, right? Remember the derivative of ln y is 1 over y. And then when you derive y, it's just dy over dx. Fix this. Dy over dx. Okay. So now you can take the like terms, the dy over dx out because it's a common factor between the two. And now you're basically expressing this expression in terms of dy over dx. What you get is basically 1 divided by this whole thing here. 21 y squared plus 3, then y squared, right? Divided by y, so it's just divided by y. Right, so that is what you get. Now you can simplify this expression obviously to get the y out here. And you multiply by y in the numerator and denominator, then you get y divided by 21 y cubed plus 3 ln of y squared. Right? And this is what it's equal to. And now when you evaluate this at a value of at the points that was given, because remember that's what we're trying to do. Let's write that down. So you're basically evaluating that at the point from 7 to 1. Okay. Evaluated at 7 to 1. When you evaluate that, at that point, obviously this definition has no x there, so you don't need to plug in the value of x, but you do need to plug in the value of y. And when you substitute that in, you will get 1, you should get 1 over 21. Okay. Sorry again, there was some noise around. Okay, so yes. So when you substitute this the points inside the derivative of this the inverse of this function, this is what you should get. Okay, so I'll leave the calculation to you guys. This should be straightforward. Now, if you move on to sub question 3 now. So what are we asked here to find? Now here we're asked to find the equation of a tangent line to the inverse, right? To the it's my mistake. It should be to the inverse of f of x at that point, right? That is already we've already done sort of half of the work in sub question 2, right? So now all we have to do is write the equation of the tangent line. And remember, the equation of the tangent line is just y, right? Y minus get expression. Equation of the tangent line is y minus y1, right? Y minus y1 is equal to the slope multiplied by x minus x1. And x1 is the point, right? Just and now when you substitute in the values, x1 and y1 are just the coordinates of the points that we're given. So when you substitute the value of y1, you get y minus 1. Our slope has already been calculated, which is that. Right? 1/21. And multiplied by x minus x1, which is just 7, right? And then when you simplify this expression, what do you get? When you simplify the expression, you just get y is equal to 1/21 x plus 2/3. Okay, so I'll leave the simplification process to you guys because you should be able to do at this point, right? Yeah, that's it for this question, right? Let me just see if I didn't omit anything. Right? Yeah, I think that's it. Okay. So thank you for that. Now, moving on to sub question 4. Okay. So for sub question 4, we are asked to determine if the IVT applies to some function f of x given as x plus 1 divided by x1 minus 9 on the interval from 0 to 5, right? And we are asked to justify our answer. Okay. So again, you guys remember sorry, just give me a minute. Yes. You guys remember what the IVT is, and you remember where it applies. Okay. But now you know the rules for the application of IVT, right? So we can let's go back to our original thing. So so the rules that we're given here, for example, for this first question here is that the function has to be continuous, right? So it has to be continuous on the interval of interest, right? But now, what's could be the problem for this function, function f of x here? Because remember, the function that we're given is f of x is equal to x plus 1 divided by x squared minus 9, right? And we are asked to check for the application of the IVT on the interval from 0 to 5, okay? So does that make sense for this particular function? Let's look at what does the function need to have for IVT to be able to be applied to it, okay? So we just said that it has to be continuous everywhere, okay? And what that means is that any point in this interval should be able to find a value in f of x, okay? But as you can see, when you plug in the value of 3 here in the denominator, you have 3 squared, which is 9, minus 9, which makes the denominator 0, which is not allowed in our analysis, right? So the value of 3 makes the denominator 0, which makes the function undefined at that point. And 3 is included in the interval, right? So what we can say here is IVT does not apply to this function. It does not apply to this function because the function is discontinuous. At the function is continuous at the value of 3, which is part of the interval of interest, right? So here, this is an interesting problem because you can clearly see that we know what IVT, or rather we know in what case IVT applies to a specific function. And for IVT to apply, the function has to be continuous everywhere within that interval. But the problem with this interval, as we just said, is that we have a value of 3 that makes this function discontinuous at when you plot it at that point 3, right? So the function is not defined at that point 3, which is a problem because the function should be continuous all throughout the interval for IVT to apply in that interval. For us to even start applying IVT to the function, we need to figure out if the function is itself continuous everywhere in the interval of interest, right? So that is a very, 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 very important point, okay? So when you're given a function like this, you need to be careful, okay? The trick would be, okay, let's evaluate quickly the value of f of x at 0. Let's evaluate the value of f of x at 5, and then we check if the sign changes, and immediately we can use the conclusion of IVT that there must be some point in the interval at which the f of x is equal to 0. Okay, so that's the trick. You don't forget that one of the conditions for this IVT to be applied is the continuity of the function. Okay, so pay attention to that when you have specific problems. Right. Okay. Now, we have a second problem here, which is giving us the equation x squared is equal to square root of x plus 1, and we are asked to find that using IVT, this equation here has a solution somewhere in the interval from 1 to 2. Okay, so first of all, the first thing that you should be looking at is the function continuous on the interval that we're given? Okay, so we need to evaluate that. Is the function continuous, right? So the first thing that we can note already is f is continuous. F is continuous everywhere. Everywhere in the interval given, right? It's continuous everywhere because if you see any value that is between 1 and 2, you plug it into there, it has to be defined. So, and it is defined, right? So we've gotten that out of the way. So now, secondly, we have to look at now what are the values that this function gives us at 1 and 2, and is there a change in sign, right? So let's define some function f of x such that it's equal to x squared minus minus the square root of x plus 1. Okay, so we are defining a function f of x as that, okay, to sort of make our life easier. Now, and we are trying to find the value of x that makes this true, equal to 0. So now let's evaluate f of 1. What is f of 1 equal to? When you substitute the value of 1 here, you have 1 squared, which is 1, minus the square root of 1 plus 1, which is 1 minus the square root of 2, which, as you can see, is less than 0. Okay. Okay, so now let's evaluate the value of f of x now at 2. What happens at 2? When you plug in the value of 2 there, you have 2 squared, which is 4, minus the square root of 2 plus 1, which is 4 minus the square root of 3. Right? So 4 minus the square root of 3. Okay, which you can clearly see is definitely greater than 0. Okay, so since, right, we have f of 1 and f of 2, since these two are of opposite signs, we can therefore conclude, right, these two are of opposite signs, so we can therefore conclude, right, by the IVT, right, that there exists some value C, right? So let me just copy this, right? We can conclude that there is some value C that belongs to the interval from 1 to 2, there is some value say that belongs to that interval such that, okay, when you plug in C into that function, right, such that f of C, right, so the function evaluated at that point C is equal to 0. Okay, that is the rule of for IVT, right? So now what does that exactly mean for our function here? Let's see what that means. It means that when you substitute C into that, so you would have C squared minus square root of C plus 1, which should give you a value of 0, right? And what that means is you need to have this equality. C squared has to be equal to the square root of C plus 1 for the difference to be equal to 0. Okay, so that's what IVT definition tells us. Now, that covers so that covers sub-question B, right? So now let's look at sub-question C, which is asking us to prove using IVT again that this function f of x, which is a polynomial, x to the 7 plus x to the 5 plus x cubed plus 1, has exactly one solution, right? So we can clearly see that, again, remember the rules for our IVT to apply, okay? So we can clearly see our function f is continuous everywhere. It's a polynomial. Polynomials are defined everywhere. Any value of x that you give in here will give you a reciprocal, sorry, what I mean is any value of x that you plug it into the function f of x here will be defined, will give you a value f of x, right? So it's continuous everywhere, right? Also, now, the second point that we're trying to do is we're trying to see how the IVT would apply to this particular polynomial, right? So, and the way we do that is we choose a value of f of x, right? Here we're not given a specific interval, so basically we can use any value of x. So let's choose a value of x such as -1, for example. Right? And when you substitute this into this equation here, you will see that it gives you -2, right? -1 to the 7 is -1, -1 to the 5 is -1, -1 to cubes is -1. So you have -1, -1, -2, -1, -3, +1, -2, right? So when you evaluate the function there at -1, it gives you a negative value, which is less than 0, right? So now when you evaluate it at some other value now, when you evaluate it at some other value, such as, for example, 0, you have that is equal to 1 now, which is, as you can see, greater than 0. And what that means is that we have a change of sign. So we have a change of sign. Just for clarity, I will change here the question to proving that this has at least one solution, okay? Which is what we'll do. There's there is a second part to this question that actually sort of proves that there is exactly one solution, but since it's using a part of the course that you guys have not covered, we'll just stick to the parts, to the IVT part, which is what you guys have done already. So we've already found that between 0 and -1, there's a change of sign, right? And therefore, since the function is continuous, we've proven that by the IVT, right? There exists, right? There exists some sort of value f of c. There's some sort of value c such that when you substitute it into the function, it should give you 0. And that c belongs to the interval, right? Our interval here is -1 to 0. Okay. So later when you guys deal with Rolle's theorem, well, we can look at the second part of this question, but for now, we will stick to IVT, which is what you guys have already done. Okay. Yeah. So that is it. You should be able to go through what we've done, everything here, and sort of try to understand it on your own. Okay. So I think like that would be very helpful. Okay. And yeah. So try to understand this whole thing on your own and see if it makes sense to you. Okay. So thank you so much for I guess for watching the video whenever you will be watching the video, and good luck for your assessment. Right. Thank you.